While the James Webb Space Telescope has found an Earth-sized planet since its launch in December 2021, it has been focused on reconstructing the universe's history by discovering unknown stars and planets. The James Webb Space Telescope has been quite successful in its mission of investigating the potential for life on new planets. Recently, the telescope discovered a potential habitable Earth-sized planet for the human race. How did James Webb come about the discovery of this Earth-like planet? What is so special about this planet that scientists believe it could be the next Earth colony? Join us in this video to explore how the James Webb Space Telescope just discovered a habitable, green, musically resonant planet. The James Webb Space Telescope, JWST, is the most sophisticated telescope exploring our universe. It is equipped with high-resolution and highly sensitive instruments that help it view objects too old, distant, or faint for its predecessor, the Hubble Space Telescope. The JWST uses infrared astronomy to conduct investigations across different fields of astronomy and cosmology. The telescope is tasked with the primary functions of observing the first stars, the formation of the first galaxies, and the detailed characterization of potentially habitable exoplanets. Working in line with this mission, the JWST has been pivotal in discovering a few habitable exoplanets, as we will see as we move further in this video. WASP 96 is one star that is the talk of the town in the scientific community. It is a yellow dwarf star that has excited space enthusiasts because it holds the possibility of being habitable by humans. It is similar to our Sun but differs by being cooler and older. This last bit of information came as a surprise to many scientists when they found out it is located about 1,150 light-years away from our planet in the southern constellation called Phoenix. The main sequence star is known for hosting at least one exoplanet, the most popular one being WASP 96b. We didn't know about this star until 2013 when it was discovered by the Wide-Angle Search for Planets, WASP. WASP is an international consortium of many academic organizations that have come together to perform an ultra-wide-angle search for exoplanets using transit photometry. WASP employs a collection of robotic telescopes to survey the length and breadth of the sky simultaneously. The telescopes monitor thousands of stars at an apparent visual magnitude from about 7 to 13. The program has two continuously operating robotic observatories that cover the northern and southern hemispheres. The first, Super WASP North, can be found at Roque de los Muchachos Observatory on the island of La Palma in the Canaries, while the other, Super WASP South, is at the South African Astronomical Observatory in South Africa. WASP comprises the Isaac Newton Group and 6 universities from the United Kingdom. WASP observatories employ high-tech instruments for follow-up characterization. By using Doppler spectroscopy, WASP has been able to determine exoplanet masses. Each observatory of the program has an array of 8 Canon 200mm f/1.8 lenses. WASP telescopes are mounted on an equatorial telescope mount built by Optical Mechanics Incorporated. The Canon lenses come with a large field of view, giving each observatory a massive sky coverage of 40 degrees. The observatories operate by continuously monitoring the sky and taking images approximately once per minute. They gather up to 100 gigabytes of data per night. These observatories use the transit method to measure the brightness of each star in each image. Furthermore, small dips in brightness caused by large planets passing in front of their parent stars can be searched for. One of the notable exoplanet candidates of WASP that has been identified as holding the possibility of being habitable is WASP 96b. This gas giant exoplanet has a mass of 2.48 times that of Jupiter and is situated 4.53 astronomical units away from its star, WASP 96. From the data obtained from the WASP observatories, we know that this planet orbits its star every 3.4 days and is about 1,120 light-years away from us. The scientific community learned of the existence of this planet in October 2013. The James Webb Space Telescope has studied the planet, and from what the JWST tells us, water can be found within this planet's atmosphere. It doesn't stop there. James Webb also discovered evidence of clouds and hazes in WASP 96b's atmosphere. This discovery came as a shock to NASA and the rest of the astronomical community because this planet was initially thought to be free of clouds. We have to thank the high-precision cameras of the JWST for changing this narrative. The distance from which WASP 96b orbits its star is just 17% of the distance between Mercury and the Sun. The discovery of water in WASP 96b means that exoplanet enthusiasts have been right all along. There is a possibility that we could have Earth 2.0 in one of these exoplanets. Beyond the excitement that comes with this discovery, scientists have been forced to ask an important question. How can water be found in a very hot planet like WASP 96b? To answer this question, we must evaluate the history and chemistry of this amazing planet. WASP 96b belongs to a family of hot Jupiters, which are gas giants known to orbit very close to their stars. From what scientists have observed over the years, these planets are believed to have formed further out in their planetary system where water seems to be abundant. Then the planets migrated inward due to gravitational interactions with other planets or their stars. The effect of moving close to their stars is that they experienced intense heating and tidal forces that inflated their atmospheres and altered their chemical composition. The presence of water in the WASP 96b atmosphere has made scientists hypothesize that it retains some of its original icy material during its migration. Another notable member of the WASP family of exoplanets is WASP 76b, classified as a hot Jupiter planet. WASP 76b can be found in the constellation Pisces and orbits its host star, WASP 76, within 1.8 days. The exoplanet is positioned at a distance of 0.033 astronomical units away from its star. WASP 76b is far bigger than our planet, with a mass about 2.92 times that of Jupiter. Although it is not an Earth-sized exoplanet, our descendants could one day live on this planet. Discovered on October 21, 2013, WASP 76b is the only known planet in its system and has an estimated equilibrium temperature of 2,190 K. Most of what we know about this planet was obtained from data acquired by the Hubble and Spitzer space telescopes. From investigations, it was discovered that there is evidence of titanium oxide and a small amount of water in the planet's atmosphere. When astronomers used higher resolution spectra to observe the exoplanet, they found that ionized elements such as lithium, sodium, potassium, magnesium, calcium, manganese, and iron were present in its atmosphere. Further investigations revealed the presence of barium in 2022. In describing WASP 76b, scientists say it is cloudy, predominantly gray, and exhibits thermal incandescence. WASP is not the only successful space program that has helped uncover exoplanets. The Transiting Exoplanet Survey Satellite, TESS, is another remarkable space program managed by NASA that has been pivotal in searching for and studying previously known exoplanets. TESS is a space telescope that searches for exoplanets using the transit method in an area 400 times larger than that covered by the famous Kepler mission. Launched on April 18, 2018, TESS was designed to detect about 1,250 transiting exoplanets orbiting targeted stars. It makes use of an array of wide-field cameras to perform a survey of 85% of the sky. It is equipped with 4 wide-angle telescopes and associated charge-coupled device, CCD detectors. The telescope operates by transmitting observed data to Earth every 2 weeks. The development of TESS has made it possible for us to study the mass, size, density, and orbit of a large group of small planets, including a small sample of rocky planets in the habitable zones of their host stars. Furthermore, we can say that TESS helps to make the work of the JWST easier because it provides prime targets for further characterization by the James Webb Telescope. Unlike the Kepler telescope and ground-based telescopes that have mainly detected large exoplanets, TESS has helped us uncover planets around distant stars that are too faint for characterization. As of November 2022, TESS had identified 5,969 candidate exoplanets, of which only 268 had been confirmed and 1,720 had been dismissed as false positives. LHS 475b is among the exclusive list of confirmed exoplanets. LHS 475b exists within the system of the red dwarf star LHS 475, situated 40.7 light-years away from the solar system. LHS 475 can be found in the constellation Octans. LHS 475b is the only known exoplanet in its system and was initially found in the transit data from TESS before the instrument of TESS confirmed it. One reason LHS 475b has held the attention of scientists is that it is close in size to Earth, at 99% of its diameter. However, a disparity occurs in temperature because it is much hotter than our planet. A visit to the exoplanet would find one experiencing an equilibrium temperature of 586 Kelvin. Scientists say that if we were to assume that this planet has little to no atmosphere, its dayside temperature would be estimated at 748 Kelvin. Unlike most confirmed exoplanets, LHS 475b has a very short orbit around its star, completing an orbit within 2 days, and we suspect this planet is tidally locked. This means that only one side of the planet faces its star, basking in permanent daylight, while the other side is covered in pitch darkness. LHS 475b holds a special place in the history of the James Webb Space Telescope because it is the first extrasolar planet to be confirmed by the JWST. Moreover, regarding radius, it is very similar to Earth. A look at the data obtained from the Webb telescope shows that LHS 475b is a rocky world. On the first look at this planet, scientists were astonished by its unique atmospheric spectrum. Another surprising thing about this exoplanet is that it lies closer to its star than any other planet in the solar system. LHS 475b was observed by JWST using 2 transits of the exoplanet. Each transit lasted 41 hours, providing James Webb with 21 hours of observation. Thanks to NASA for creating the JWST, as it is the only known telescope scalable for observing and characterizing the atmospheres of Earth-sized exoplanets. After studying LHS 475b's transmission spectrum, the Webb telescope found out the composition of the planet's atmosphere. Although the data is still being processed and the results are yet to be out, we now know what is not inside the planet. From the data obtained so far, scientists hypothesize that the atmosphere is filled purely with carbon dioxide. Thus, we need more precise measurements to differentiate a pure carbon dioxide atmosphere from a non-carbon dioxide atmosphere. The Webb telescope has made us aware that this planet is a few degrees warmer than our planet. This fact is proof that we should explore the planet better because it shows promise of being a habitable colony for the human race. If scientists were to discover clouds on this planet, then we would be forced to conclude that it is more like Venus, which had a carbon dioxide atmosphere. With more observation data expected to be presented in the coming days, we will finally be able to confirm some of these hypotheses. The first discovered Earth-sized exoplanet reported by TESS is HD 219497449b. The discovery was announced on April 15, 2019. HD 219497449b orbits the orange main sequence star HD 2199749, which can be found in the constellation Reticulum. In addition to the remarkable findings from the James Webb Space Telescope and TESS, ongoing advancements in exoplanet research continue to offer fascinating insights into our universe. The field of exoplanet science is evolving rapidly, thanks to a combination of ground-based observatories, space missions, and advanced computational techniques. Recent developments in observational technology have improved our ability to detect smaller and more distant exoplanets. For instance, next-generation ground-based telescopes, such as the Extremely Large Telescope, ELT, being constructed by the European Southern Observatory, promise unprecedented resolution and sensitivity. These advancements will enhance our capacity to study the atmospheres of exoplanets in greater detail and potentially identify biosignatures. Moreover, the use of machine learning and artificial intelligence in exoplanet research is proving to be a game-changer. These technologies are helping scientists sift through vast amounts of data more efficiently, enabling faster identification and analysis of exoplanet candidates. Algorithms can now detect subtle patterns and anomalies in light curves that may indicate the presence of exoplanets, which would be challenging to spot manually. Additionally, upcoming space missions such as the European Space Agency's Ariel mission, set to launch in the late 2020s, will focus specifically on studying the atmospheres of exoplanets. Ariel aims to analyze the composition and structure of exoplanet atmospheres across a wide range of planetary types and orbital distances. This mission will provide crucial data to understand the diversity of planetary atmospheres and their potential habitability. In the broader context of planetary science, researchers are also investigating the potential for life on moons within our own solar system. Moons like Europa, Enceladus and Titan are known to have subsurface oceans or liquid lakes, which could harbor conditions suitable for life. Missions to these moons, such as NASA's Europa Clipper and the upcoming Dragonfly mission to Titan, are expected to provide valuable insights into the potential for life beyond Earth. The convergence of these various efforts and technologies is driving an exciting era of discovery in astronomy and astrobiology. As our tools and techniques continue to advance, the search for habitable exoplanets and extraterrestrial life becomes increasingly promising, expanding our understanding of the cosmos and our place within it.